Okay. So now we're near ending. We've got two little sections to cover. We're going to cover today use substitutions. And we're going to cover chapter 8, section 2, which is integration by parts tomorrow. These two sections actually encompass basically all the techniques of integration, right? You will do some extra stuff in 1080, but everything that you do is basically just either an algebra or a special case of use substitution or parts, which I'm going to talk about tomorrow. So hopefully you all will get a leg up in 1080 when you have to do that. Now, so here's kind of the big thing we've been focusing on is this. I'm going to call this like Marion. This is a big sort of focus of what we've been doing. Find this integral, and of course, the function is positive, which represents an area. In the case that I've drawn here, it's a sine over a net area, where it's a positive part, it's negative. Number one, we started this way, the definition. We saw that this was incredibly tedious. Even when this limit exists, we have it in this easier form where we break the interval up into evenly spaced pieces and choose some regular points to determine height. So we moved on to this too. This is the fundamental theorem of calculus, and it made our lives oh so much easier because now doing this complicated limit reduces just to doing this. But here's the rub. You have to be able to find this, the antiderivative. And frankly, in some cases, you just can't do it. You just can't do it. In which case you revert back to this, not necessarily taking the limit, but making breaking this up into very, very maybe a million little subintervals and doing an approximation. You will look in 1080 at some of these things as well as how to approximate it when you actually can't find this antiderivative. But practical focus for us is here's the big question. How to find how do we do that? And we've got some easy cases like the antiderivative of x squared is 1/3 x cubed, the antiderivative of cosine x is sine x, etc., etc. And I've given you some examples of things where you just can't write it, you just can't do it, right? The antiderivative is there, but you can't write it down in terms of familiar functions, e to the x squared, sine of x squared. There's a zillion of them. When this can be found, how do you do it? Basically, there are two techniques. Well, say 2.5. One of them is algebraic simplification, right? That takes you, basically back to high school. Can you algebraically simplify this and make this doable? So, for example, one of the questions I asked you on the test. And I wanted this to be from How do you do this? A lot of folks, I must admit, integrated the top and then put an antiderivative top and antiderivative. Please don't do that. Absolutely does not work like ever. Like, don't do that. But factor the top and bottom, because this is x plus 1 quantity squared and this is x times. What can I do with that extraneous x plus 1? How could you simplify this thing I'm integrating? Now, can you explain why this is progress? Well, right, I can do a little bit more algebra, right? This is 1 plus 1 over x. Everybody agree with that? Now this is something that I can, bite off here. Oh, I remember now, it was 2 to 4, I think. So this is 2 log 2 minus 1 plus 0. So I get 1 plus log. Okay. So notice I did 2 algorithms, cancel, and then I rewrote this, right? There's nothing fancy about that. It's just using algebra to get this into something, into a form where you can actually write down the antiderivative. There are 2 basic techniques that are what you might call calculus techniques. When you get to 1080, you will generalize this by doing something called partial fractions, which is an algebraic technique. So there are 2 basic techniques. They are one chain of, so what's called U substitution, or sometimes just substitution. And it is that untangles complicated things with a chain rule. It sort of inverts the chain rule once it's spread things simple. This is what we're going to talk about today. Second technique is called integration by parts. And it undoes the product. So sort of technique of integration by parts is integration. Its product rule is to differentiation. It's an attempt to do that. And U substitution basically attempts to undo the chain. So we are going to focus on this today. We'll focus on this one tomorrow. So examples here. By the way, when you see a naked integral sign with no numbers on it, this just means find the antiderivative. This what's an antiderivative for this? This, in one sense of the word, I think this is the trickiest problem. I give you a hit on this problem on the exam, and I say just see if you can guess around and see if you can find an antiderivative of 2x squared. Some people are successful in that. But how do I take the antiderivative? I can take the derivative of x. But what about e to the 2x? Antiderivative of the x is the x. Is the antiderivative of e to the 2x e to the 2x? No, it's off a little bit. Because what's the derivative of e to the two x? Right, it's e to the two x times two, so it doesn't quite fit. How do we fix that? What about this? This is, what, sine x over cosine x? Tan derivative. What about this one? By itself, you can't write an antiderivative down. It's just too hard. How do we deal with all of these in certain sense? Well, I'm gonna go ahead and I'm gonna give you the theorem. So I'm gonna arm you with the theorem, and then I'm gonna do a lot of these. So here is the theorem, substitution. I'm gonna have this kind of two parts. It's got two theorems, one for indefinite intervals, one for definite. Let you g of x, where g of x is differentiable. So and f is continuous on the range phi. I'm sorry, I'm brain. Then interval f of g of x from x to x. F. This is called a usage. And let me show you kind of the way that it helps me keep track of things. Think of this as transforming this. This is a rather complicated thing that I can find an antiderivative for. And this is much simpler. So think of it this way. What I do is, see, I want to turn this thing inside the parentheses, which might be quite complicated, into something easy. Right? So instead of g of x, I'm going to call this u. Now think back to when we were doing differentials and linear approximation. U is g prime of x dx. Remember when we did that doing the differentials? And it's the same idea here. This is u, and this bit d, and it's this one. This is for indefinite intervals. If the interval is definite, I need to add a continuity prime. Definite if u is g of x and g prime of x teens on the specific interval a b, and f is continuous on the range of g. Then interval a b of f of g of x, g prime of x, x is equal to, again, it's f of u, u, but the substitution equation tells you what to do limit g of b. So you use that substitution rule to get the new endpoints. Instead of a to b, it's now g of a, g of b, where this is your new substitution. Now, before we move on, let me ask you all this. How many of you had calculus in high school or seen new substitution? Anybody? Okay, that's good. Prefer it that way. Okay, so let's do some examples. Let's go crazy here. Okay, let's start off with, let's go through these. You can almost do this one in your head. You want to be clever enough. But I don't know how to take the antiderivative of e to the 2x yet. But I do know the antiderivative of e to the x. So I wish this were just one variable, just something instead of 2x. So do it that way. The idea is I'm going to turn this complicated 2x into the simple 2. And if this is the case, what is du? It's 2 dx. Right? Don't forget this part. And also, you need to, when you do a substitution, when you're finished with it, everything with x's has to be turned completely into u's. No extra x's. You have to excise everything. You have to turn it all into u's. No du's on the bottom, no du's on the square root, anything like that. It has to be out there just like dx. So let's see here. So there, dx is 1/2 du, right? So this becomes e to the u, and instead of dx, I have 1/2 du. So this is 1/2 integral of e to the u. And see, guess what? I know I can do that. No 2's there. It's 1/2 e to the u plus c. Now I've got to put back in terms of my original variable. One half e to the x. Let me tell you one of the most glorious things about doing the homework in this section is when you're doing an indefinite integral like this, you can always check your answer. Take the derivative of this. If you get back there, I don't care what the back of your book says, you are correct. Any questions? Okay. Let's find the antiderivative of tangent. I told you what this was before, but and I think I verified. When we were talking about antiderivative back in section 3, I just told you what it is. Check. Where do you get it? So I want to find the antiderivative of tangent x. Good idea here is often go back to the basics of trig functions. This is cosine x. Now, when you try u substitution, there are a lot of things to try. There are pieces, parts. Bottoms of a fraction, good to try. Things in exponentials, good to try. Things inside square roots, good to try. And there's only so many things you're probably going to try. Any idea for u substitution that might make things more fun? Great choice. If you make that choice, what's the derivative of cosine? You know what? Just by assessments, I think I've got this lit. Because this piece is going to be u, and this piece here is almost e. It's actually negative. Everybody okay with that? But the sine x dx jump du. So that's why this works. So this becomes the integral of negative du over u. It's negative 1 over u du. And what's the antiderivative of 1 over u? Something derivative is one of the. There you go. Minus natural absolute value, C. So I get minus natural log absolute value cosine X. And again, you can check. By the way, some books will write this way. Another way to write it. Natural log absolute value cosine X to minus 1 plus C. And what's the reciprocal of cosine? 1 over cosine is C. Some books you'll see the answer very tangent written this way, some this way, but they're the same. Let's do it that. Okay. I want to figure out what this definition is. This is well, it's not an area under a curve, like it's a signed area, because notice this, the e to the x squared part's always positive. This is negative, x is negative, and positive, x is positive, so this is in the signed area. Any ideas for a substitution, like work out well for us? So, that's great. The idea is I can handle e to the x squared, mysterious. So let's just try this. And I see, Richard, you saw a step ahead, because that piece is what we're going to get for du. And this works out swimming, because this part right here, this part here, so I've got everything accounted for. You gotta be a good accountant here, make sure you account for it. And this becomes, well, I get e to the u. And everything else is du. Oh, that's easy. But there's one more thing I need to do, and what's that? That's right, I need to change my limits. And so the way I remember this is, in the old days, I'm integrating with respect to x. X is minus 1, and x is 4. In the new days, I've got u. So if x is minus 1, what is u? 1, right? So in the old days, negative 1 is x, so that becomes u as 1. In the old days, x is 4, so what does u become? 6. So this becomes e u value over 116, so it's e to the 16 minus. This problem, let's do a little twist on this problem here. Take this again. Then I'm going to generalize this. First, we do this. Well, you know, u equals squared work 4, so again. I get the same bit here. This is du, du. It's all working out the same. What's my new top limit? Could be saying 4. What's my new bottom limit? 6. Wow. Right, but I mean, is there something about this function that I could have told that in the first place? Is there something odd about this one? It is a pattern modifier. So this doesn't surprise me. And in fact, I'm going to do an example. Let's let A bigger than 0. F of x on U of x. In this example, I've got 2 functions. One of them's odd, one of them's even. So let me remind you that means f of minus x minus f of x. So this is like x cubed and sine x is 4. And the even one is g of minus x is just g of x. So now I've told you all, what do you expect to get for this? What happens when you integrate an odd function with symmetric interval? What you get? You should get 0, right? I've been beating that in your heads a little bit and say, well, you know, the areas cancel out. But what I told you, in a certain sense, you're taking on faith. It's like a political statement, right? Because, yeah, it kind of looks like the areas cancel out. Here, we're going to see it's hardcore. It's true. Let's do this. Now, notice I can always do this, right? This just needs to integrate me minus a 0 and then 0 to a. Why did I break it up? Because of the symmetry of the function. Right? Now let's consider. I'm gonna leave this alone. I'm not gonna do anything with it. I'm just gonna let this ride. This one I'm gonna do a little manipulation. Here I am going to do u equal minus x, or equivalent minus u equals x. So u minus x. So that's about as simple a substitution as I can muster. Replace u with minus x. So what happens to this first piece? Well, in the first piece, what I get is, let's see, this is going to be f of negative u. And instead of dx, I'm going to have minus du. Everybody agree with that? So this first one's the only one I'm working on. Replace x minus u, replace dx with minus du. And I need new limits. What's my new bottom limit? It's going to be positive a, because in the old days, x is negative a, so negative negative a, u is positive a. And what's my new top limit on this? Still 2. And as I promised, I'm leaving you out alone. Now. There's negative outside here that I'll pull out. This minus sign allows me to reverse the order of integration, right? Right, see, so go from here to here, it's about flipping around. Now, the only thing I haven't used here is the fact that f is an odd function. What can I replace f minus u by? F minus u minus f. This 0 to a. I'll pull that minus sign up front. This is integrate f from 0 to a. This is minus integrate f from 0 to a. Because the red integral, the black integral, the same thing. So you subtract the red integral, black integral. For even functions, you get something similar. So let's continue the example by looking at what happens at g. If you integrate g of x from minus a to a, I'm going to again break this up. Minus a to 0, g of x, x plus 0 to a, g of x of x. And I'm going to do the same thing that I did before in the following sense. I'm going to leave the second one alone. And for the first one, I'm going to do again the substitution in the minus x. So this becomes, the first interval becomes g of minus u times minus du. And my new limits, when x is negative a, u becomes a. And this is plus integral from 0 to a. Now, I'm going to bring this minus sign out in front. We're going to do the same procedure here. Plus 0 to a. And I'm going to, again, use this minus sign to change the limits. So this becomes the interval 0 to a of g of minus u plus integral from 0 to a g of x. Now we use the fact that g is an even function. What does that mean? G of negative x, g of x. So this is just g of u. So this is integral 0 to a of g of u plus integral 0 to a of x. Just like before, these two quantities are the same. I've got some function g integrated from 0 to a. Got the same function g integrated from 0 to a. This time I'm adding instead of subtracting. So this should be twice integral from 0 to a of g of x. So there's a justification of what I was telling you about functions that are even and odd. Okay. Here's an example. I'm going to go several. Let me start off with kind of specific. Um, it's one math. Now, you can do this without use substitution, but I wouldn't recommend it. Because what you could do is you could write 2x plus 1 down on your paper 17 times in a row and multiply that out. Nobody wants to do this. Right? It's going to be a 17-degree polynomial. Good luck figuring it all out. Right? The leading term, the leading term will be 2 to the 17th power times x to 17. And the last term will be 1. And what's in the middle is a mess. Right? So this can be done, but any ideas on what we use substitution? Great idea. So it might be x, for example, 1/2. So this integral now becomes this is the whole point was this is inside parentheses. The x is 1/2. Oh, I gotta change my limits. What's my new bottom limit? Right. In the old days, x is 0, so you should 1. What's my new top limit? 2. Put in 1/2 for x, I get 1 plus 1 is 2. Okay. So this is 1/2 integral from 1 to 2, u to the 17, which is 1/2 times u to the 18 over 18. Evaluate. So this is 1/2 2 to the 18th power over 18 minus 1 over 18. There you go. Now, maybe you're the most stubborn person in the world. Think, well, I can still multiply that out and do it. Let me change the game on you. What if I ask you to enumerate? Right, so now I've got the A power. So A could be 17. But if this is 17, I can multiply this thing out and figure it out. However, if A is 1/2 or 3/2 or pi or some other strange number that's not a positive integer, you can't multiply this out. Right? By the way, I'm going to put a caveat up there. I'm going to look at all powers except for if you go on just the power I don't want to have there. Students later. Not zero either. That's better than a second area. See, like, anybody wants to get what makes me negative? Right, that's essentially it, because use substitution is going to trick you something out that. We'll see as this develops why I want A to not be -1, then we'll deal with that separately. We're going to take the same strategy that we did before. If U is 2dx, so my integral becomes U to the A power and but dx is 1. So the antiderivative of this is 1/2 U to the A plus 1 over A plus 1. What happens to the formula of A is -1? Well, if A is -1, I've got a serious problem. So the answer to my problem is 2x plus 1, the A plus 1 power over 2 times A plus 1. As long as A is not equal to 1. What if A equals me? What happens? That's not work out very well. If you use 7 next 6 power, now you're going to have trouble. So what happens today is -1. Well, I mean, we can pick this up where we left off and you can just start over again. So this is 2x plus 1 to the -1 power. And again, the same substitution works. Like I said, you go through most of these steps. So this is going to be u to the -1, 1/2 du. So this is 1/2, 1 over u, which is 1/2 natural log absolute of u. C actual. Again, I can't emphasize enough. You should work a lot of these problems because it takes a while to get kind of a feel for what new substitutions to pick out. The good news is just try something, right? And if it doesn't work, it doesn't work. There's only so many things that you can try. Just be stubborn. When you get your answer, if you take the derivative of your answer and you get what you started to integrate, then you're right. Okay, so let me give you some examples where you might have to like think about it a little bit more. What if we have there's one value to yes, where you already know the antiderivative. You like tell me what it is. What value of A other than zero? What could appear next to the x squared that you know what the antiderivative is? One. What's the antiderivative of dx over x squared? It's the inverse tangent of x. What can we do? Well, you know, don't you wish this was one? So do I. So let's do this. So this is 1 over a squared. Everybody agree with that assessment? There's only one thing wrong. Now I've got +1, but it's not x anymore. Dang it. It's x over a squared. Anybody think the u substitution might fix this? Fantastic. Right? I just want this to be just the variable. So try it. Or x. Okay, let's see what that finds. Let's see, the x is a u. That's going to be u squared. Right, okay. Now notice this a will cancel one factor of this, and if it's 1 over a du over u squared plus 1. And what's the antiderivative of 1 over u squared plus 1? This is one we know. But my original was in terms of x, so I want this in terms of x. So this is 1 over a inverse tangent x over a plus constant. And again, check it. See, that's technical. Any questions? let me illustrate something. This is an example that's a little bit more sophisticated. You need to get in right now, but so I'm gonna do this quickly, but this example is to point out that this is sort of unusual, and this leads into something called trig substitutions that you all will do later. But sometimes a clever substitution works, sometimes a substitution is a little bit out of bounds. Now, I know what this answer is. I know that I should get inverse tangent. Can anybody think the substitution that may work? It's natural for you to say, well, let's try x squared plus one, u equal x squared plus one. But then the du, if u is x squared plus one, what's the du going to be? 2x dx, and there's no 2x here that don't count. Like that. Take the derivative of that, you get 1 over y, which gives you encouragement. Then what do you do right there? You gotta multiply by the derivative of y. That kills you. Right? There's no 2x. This is a substitution. I didn't write this in the form of u equals something x, but actually the substitution is better. What's dx? What's the derivative of tangent theta? Secant squared theta. And don't forget your d theta. So just plug in. Dx is secant squared theta. D theta. And what do we get on the bottom? I get tangent squared theta plus 1. Which looks like I've made it worse, but I haven't. Anybody know what another name for tangent squared theta plus 1? Right. This is secant squared theta. And notice the secants cancel, secant squares cancel. And this is. Okay. So it's 1 d theta. Now, I don't know much, but I do know that the antiderivative of 1 d theta is theta plus c. So my answer is theta, which is disappointing because I want to turn it back. But notice that inverse tangent of x is equal to theta. So I do that replacement there. So there's a substitution that's a little out of the box. It took advantage of that trig identity that you noticed and allowed me to cancel. Sometimes a little cleverness. This one's a little bit more routine. This also. What if we what if I should do this? Well, of course, it's natural to say, well, I mean, I can't just, please do not write cosine of the 4th over 4, right? There's no way that works. Because when you start doing the chain rule, so don't do this. You don't have to take the derivative all the way, check that something's wrong. If you take the derivative of this, it's going to be 4 cosine, 4 times this cosine cubed, right? But then you're going to have a sine. The derivative was inside. There's no sine. Right? So there's no way this works. And you seem to have the same problem here. If you like what unit with cosine x, then it doesn't appear to be sine. However, substitution unit for sine x doesn't. It's a little hard to say. Anybody explain why sine x will work? Does anybody see the sign in there now? Well, that's right, but where's the sign to substitute? Be like ace of base. See the sign? Okay. Right, okay with that? So let's write this way and see. This is a little bit clearer. Now let's try that. U equal sine x. What's the u? Cosine x. Now this is. This is. Well, I'm using it. Oh, and I think that's something you can do. This is. One. So I've turned this actually into a polynomial. Let's give it a polynomial. So I get u minus 1/3 u cubed plus constant. And what is u? It's sine x. Sine x minus 1/3. Any questions? Let me give you all, and this will help you in 1080 as well. Let me give you all kind of a bit of advice. It may save you some tears later. So when you do this example, I'm going to do this 3 ways. Here's how I'm going to do this 3 ways. Well, note that identity exists, right? It's the famous double line thing. 2x is the same. Okay. How do you all want to do this problem? What's one thing that you? I say use substitution straight up on this thing will work. U equal 2x. How about that? And they'll turn this into a sine U if I can pull this off. I can make it dx get out. So dx is 1/2 du. This becomes sine of u 1/2 du. And what's the antiderivative of sine u? One half cosine u plus 1/2 cosine u. Looks like that works. If I take the derivative, I get my sine ux. Now, another thing I can do, and instead of 2 and 3, I really should call this 2a, 2b. What should I use for my u here? If I do that, sure. Why not? You're doing your homework. Don't be afraid any doesn't work. But this one, let's get you was. This is going to be 2. There's u, and there's d. Works out really nice. And what's the antiderivative of 2u? Pick it up. So this one I get sine squared. But wait a minute. Couldn't I also do this? This one's, I think, the choice made for sine x is probably the easiest one. But you can certainly do this. So now what happens is this piece right here, sine x dx is negative du, and the rest is 2u. So this is minus 2 du. Right? 2 cosine is your 2u, and then you get minus. This should be minus u squared plus minus cosine squared of x. And this is where the tears start, because you look at the back of your book, which is not always good, you like to say correct. If you look at the back of the book, check the answer, and these are all 3 different, right? All right, one answer is minus 1/2. One answer is sine squared x plus. Another one is cosine squared x. So I explain why these two are the same. Well, the reason these two are the same is sine squared x is 1 minus cosine squared x, correct? So I can rewrite this as minus cosine squared x plus 1 plus c. So this 1 plus c should be this c. Nobody said that these constants have to be the same, even though I used the same letter, and your book will too in their answers. This constant can be any. And this shows the way they, if you use both of these, how they relate. Right? There's also a trig identity. It says that cosine squared, sorry, cosine 2x is equal to 2 cosine squared x minus 1, and it's also 1 minus 2 sine squared x. And so if you replace cosine 2x with either of these, you will get those. So the point of this example is this. Here, I use 3 different u substitutions on the same problem, and I got different looking answers. All of my answers differ just by a constant, but they look strikingly different, right? So if you're not getting exactly what the back of your book says, the best thing you can do is take the derivative of your answer, and if you get back where you started, you've done it right. Okay, any questions? Okay, how about, let's do this one. Okay, somebody suggested use substitution here. And I'm gonna tell you, Rome's not built today, right? Would this be better? Can somebody explain to me why this problem is better if that stupid plus 2 wasn't there? Why is this an easier problem? Word of warning. The substitution u equals x never works. Somebody explain why. That's right. You just, everywhere you see an x, you're replacing the u. So if you couldn't do it with the x in it, changing it in u, I'd be able to do it. Surprisingly, u equal negative x does work sometimes. U equal 1 over x, u equal 2x, those work to get straight up u places. But forget u substitution for a moment. What would be better if that was just an x? What could you do? You could do the separate pieces, right, and divide out and do this. But it's not. There's an x plus 2 there. That's my inspiration. Let's turn that x plus 2, which is making my life difficult, into a single variable. By the way, you certainly could divide by x plus 2, but it's a work process. What's the u in this case? 1 dx. So my du and dx are the same thing, so that's good. Now, this substitution, how am I going to get this top taken care of? Well, this substitution is invertible in the sense that you can solve for x. You just do that. So everywhere you see an x, just put in a u plus 2. Or, well, u minus 2, I guess. And now I know that this is work because I've got everything in terms of u. So it's just a matter of multiplying this out and simplifying. This is u squared times 4u plus 4 plus u minus 2 plus 7 plus u. So this is u squared minus 3u. And this will be plus 9, I guess. So now that I've turned this into a different problem that I can do. This is the integral of u minus 3 plus 9 over. So what do I get? 1 half squared minus 3u plus 9 natural log of absolute value u plus constant. And since this is an indefinite, we know I need to put back in terms of my variable x, which was u is x plus 3. And the u rule applies here. It's a pretty short. It is certainly you could multiply this out and simplify it, but unless there's some compelling reason to do so, and there isn't really here. I don't know about you all, but I've always wanted to know what the antiderivative cosine x squared x is. Now we change. So let's see. By the way, don't be afraid to take intermediate substitution, right? If you do a u substitution, you might turn into something a little simpler that you have to do another u substitution in another one. It turns out that if you do that, you could have done it in one, but don't be afraid to make small steps. So let's try that. It's tempting because that cosine x is on top, isn't it? It's going to work. No, because I've got my sine x linked up with that x. My sine here is actually bottom. So I don't think this is going to work, but that's certainly something to try. That's a good idea. U is bottom, right? It's a good choice. But here's what happens. This is 2 sine x cosine x. Yeah, it's too much here. Don't be afraid to try something a little bit simple. Kills you is a square, right? When you take the chain rule, you get that extra. We'll give you the same u. Because if you're going to use u equals sine squared, you might as well tack on the 1 as well, because the 1 disappears when you take the derivative. Unless there's some other example where it might not. U equals what? Let's straight up sine. And the key is, and you've always got to be mindful of this, is you've got to get that du taken care of. And this doesn't, right? So this becomes, well, it goes to you. Now, does anybody know the anti-rate 1/1 plus u squared? There you go. This is inverse tangent. So we have some sense. And I guess my substitution was sine, so this should be the inverse tangent. Sine x. How about this? Antiderivative of natural log x divided by square x. That's a great idea. What inspired that? If we do that, what's my du? 1/x dx. And so there I've got it. This is du. And this. So this much easier. This is 1/3. You do, let's see. So this is 1/3. Natural log x quantity cube. And you see, there's magic going on, because this is something that before use of stations really kind of got why to do this. So it's not that x. So like this. Fill the sprout. What's my d going to be? plus 5x. Yep. All right. Dx. So this is gonna work. There you go. This is 5 times x4 plus x. So this piece right here this is 1/5 in 45 calculations, and this is useful. So this new interval now becomes 1/5 u squared. And what we gotta do? What else we gotta do? We gotta change the limit. What's my new bottom? Right. In the old days, x was 0, so in the new days, u is 3. What's my new top? Right, it's just whatever you get when you, in the old days, x is 1, so you put in 1 here, and whatever you get, it's 4 and 5 halves, which is 13. So 115 here, evaluated from 13 pounds, 13 pounds. So this becomes 1/3 and 1/5, right? Because it's going to be cubed over 3. 115, 13 halves cubed minus 27. Whatever that makes. What do you ask about the 115?
Yeah.
Yeah. So forget about the 1/5 just for a moment. The antiderivative of that is 1/3 u cubed, right? Now put that in 115. And this one illustrates a couple of things. We're not brainstorming. This illustrates sort of kind of a good way to do this as well. This is kind of hard. And this one is like, without use substitutions, think about this. Right? This is, my goodness, 1 over the square root of x plus square root of 2 root. I don't care. But actually, let me make one cosmetic change here. Let's go do this. What's one of the most obnoxious things about this problem? How many of you are fans of fractional exponents? Nobody likes fractions. I mean, don't you wish that were like x squared and x cubed instead of that? better to deal with. Anybody think of a substitution where I can replace, I can make a replacement and I can turn this into integer power to be instead of these fractions. So I want x to the 1/2 to be an integer power of u, and this would be an integer power of u. What'd you say? What's this? Fantastic. So here's my thinking. My thinking is this thing is going to be u cubed, and this thing is going to be u squared. It's going to be easier to handle. Everybody see the idea behind this? But there's an even better way to write this. First of all, it's easier to take the derivative of that thing. And second of all, everything's now your dx is completely determined. What is it? If I let x to the 6, what is dx? Six u 5 d. Everybody okay with that? Whenever, almost every time, if I can, instead of doing a u substitution, do an x substitution. So here I've solved for x instead of having it in terms of u. It almost always works out better, right? Because now you can directly substitute in the dx, and it's easier to manipulate. You don't have to tiptoe around as much as you do in a regular u substitution. So let's see what we have here. Notice, let me also notice that, I'll make this notice here, x to the 1/2 is u cubed, and x to the 1/3 is u squared. So putting all my pieces parts in here, this is x, or this is u cubed, this is u squared, and then I get 6u5. Okay, I want to make sure everybody's good and caught up with me there. Any questions on that? Okay. Y'all are ready to move forward. What's the next thing we should do? What's one obvious thing? It's an algebraic. You should always do algebras. There is a factor of u squared running this whole thing. Get rid of it. Right. This is actually 6 u cubed over u plus 1. Going the common factor of u squared. Now, what should I do now? You know, I think that we can all agree in here that I've now made this unholy mess look a little better, but I'm still a little bit stuck. No substitute. Any ideas on what I can do? This is similar to one we did before. So let's try this. Let's let z, new substitution, be the bottom piece. I want to turn that into a single piece so I can divide. So dz is what? 1 du, 50 du. So let's see what happens here. Well, now this becomes, well, let's see. And du and dz are the same thing. That's good to go. What about the 6u cubed business? What am I going to do with that? I've still got a 6u cubed left over that I've got to take care of. I've got these taken care of. There you go. This is another one of these invertible substitutions. It's really nice. This is 6 z minus 1. And that sounds like death knell. If I multiply this out, I get 6 z cubed minus 18 z squared plus 18 z minus 6 all over z. Now, this is one where I'm describing the seven. This is going to be 6z squared minus 18z plus 18 minus 6 over z. So now we start the process. Antiderivative, 6z squared should be 2z cubed. Antiderivative 18z is 9z squared. Antiderivative of 18 is 18z. And then you have minus 6 natural times plus constant. Now, go back into the view. But everywhere else is you have to plus 1. And for the last bit of glory on top of this, you got to go all the way back to X. What was U? It was X to the 1/6 power. So this is 2. X 1/6 plus 1 U minus 9 X to the 1/6 plus 1 squared plus 18 X to the 1/6 plus 1 minus 6 natural log absolute value X to the 1/6 plus 1 is constant. Now let me make it clear. Number one, we did a U substitution here. We didn't have to do that. We could have divided out and had this just in front of you. Right, so you could divide out, and then what you would have is you would have this in terms of U instead of U plus 1. If you multiply this out, then you would get what you would get here if you divide it. The point is these problems can give different answers. Notice, instead of, at this point right here, instead of 18 times X to the 1/6 plus 1, I could have just written 18 times X to the 1/6. Anybody explain why? If I multiply this out, this is 18 to the 1/6 plus 18. That's a constant. I can absorb it into here. So your answers can look slightly different, but they should vary just by a constant. Do I see what I'm saying? And number two, you should really illustrate the power of U substitution. Because I walked up to you and said, what is the antiderivative of 1 over the square root of X plus the cube root of X? Who is going to guess that? Right? I mean, look at that mess that we were able to come up with using 2 U substitutions. Okay, any questions on this? Okay, so the procedure is pretty straightforward, I think, but it does require a lot of practice. So give this a shot tonight. keep working on that. We will do integration by parts on Friday, which will be the last new thing. Monday and Tuesday are not wasted days, they're sort of review days. So you guys can bring in, and we will have another out-of-class review. You can bring in your questions, and I'm gonna try to recap. We'll talk more about the integration, anything else you want to talk about, and there will be quizzes on Monday and Tuesday. Okay, so let's take our quiz for the day.